At this point, we want to look at the total energy in a circular orbit. Now, we've talked about Kepler's first law in that orbits are in general ellipses and not circles, but circular orbits offer A, ease of feasibility of study, and B, there are circular orbits in nature. There are planetary or star systems where the orbits are very nearly circular, and thus they provide a basis for examining the more complex examples of ellipses. We're not going to do the elliptical math, okay? We're not going to do the math associated with ellipses. We're going to restrict ourselves to circles, but again, do understand that in general, an orbit is an ellipse and not just a circle. But again, this is a very instructive example, and that's why we like to do it. So, if we look at the energy in a circular orbit, what we really want to do is calculate the total amount of energy in the orbit, okay? So that's the end goal, is to calculate the total amount of energy, okay? So we want to calculate E total, all right? How can I go about calculating E total? Well, I need to get the kinetic energy, and I need to get the potential energy. Now, we already know what the potential energy of an orbit is. It's negative g times the mass of the object that's being orbited, times the mass of the object that's doing the orbiting, divided by the radius of the circle that describes the orbit. And the kinetic energy is going to be 1/2 mv squared. So we need to develop a equation for v squared, so that way we can compare it to the potential energy. Okay, so we're going to go back to the analysis that we did with Kepler's third law, and we start with the idea that in circular motion, objects experience centripetal acceleration of mv squared over r, and thus a force of mv squared. The acceleration is v squared over r, the force is mv squared over r. All right, and this is going to be equal to, in magnitude, to the gravitational force, right? And so, if we look at the capital M as the mass of the host star, say this is a star-planet system, then the capital M would be the mass of the star, and the lowercase m's would be the mass of the planet. And because we're looking at the same planet, it's experiencing a gravitational force, which is then producing the centripetal force. The masses are going to be the same, as are the radii. And so we can see that v squared is equal to g times the mass of the object that's being orbited divided by the distance from that object. And so now what we can do is multiply that by 1/2 m, and that will give us our kinetic energy. So 1/2 mv squared is equal to g m times m over 2r. Okay? G m times m over 2r. But this is not all that far from the definition of potential energy. Remember that potential energy, U, is equal to negative g m times m over r. So they're different by two things. Number one, the negative sign, and the 2 down here. So what this means is this is negative 1/2. So that means that our kinetic energy is negative 1/2 of our potential energy. Okay, that's what this is implying. So that means that our kinetic energy is equal to negative 1/2 of our potential energy. And so our potential energy is equal to negative twice our kinetic. Okay, it's equal to negative twice our kinetic energy. So if I look at my total energy, then this is going to be my kinetic plus my potential, and this is going to be kinetic minus twice my kinetic from here. And so this is equal to negative of my kinetic. So my total energy, E, is equal to the negative value of the total kinetic energy in the system. And that's a rather bizarre result, that the total energy in a system is negative, But what this means, what this negative sign means, is that the object is bound to the more massive object. So the orbit is closed. The orbit is bound. In other words, the object is not going to fly away. All right, it's not going to be able to escape the gravitational pull of our more massive object. And that's what the negative sign means. Whenever you're calculating energies in orbits, if you get a negative sign for your total energy, then that means the energy or the orbit is bound. Okay, but that's how you can show that the total energy in a circular orbit is negative, and that energy is equal to, in magnitude, the kinetic energy, but just with that negative sign. Right? We'll see you next time.